Thanks a lot, Ilias, John, and Alfonso for inviting me. Yeah, it's a good. I have good memories of teaching in front of you in different courses, with and so finally I can tell you some research as well. So very cool. Okay, so right, so yeah, the most important part. Can you guys see my pointer? Okay. So so yeah, so the most important part of my talk is this photograph of my colleague Yihong Wu. So he's this is a joint work with him, and yeah, so please remember him throughout this talk as well. Okay, so right, so the question about why, so this is a talk about mixture models, and as many of you probably familiar, and especially if you teach intro stats class, right, we really like this example about Pearson crabs. So here I present a different example, right? This is a histogram of the height of the population, height of humans, right? And you can't see much interesting stuff from just this plot alone. But of course, if you stratify by gender, then you can immediately see that actually this histogram is composed of two bumps, right? And then the question is, okay, if I just give you the histogram without the underlying truth, right, without the stratification by gender, then can you actually learn the components of the mixture? Right, so that's a basic question. So I shouldn't convince you that this is a right. So the mixture modeling is an important topic, right? Basically, whenever you have some sort of large-scale influence, right, maybe discrete, right? So the stratification plus some sort of cumulative effect of a lot of small influences, right? Gaussian mixture model becomes a good model. Okay, so now I actually was not interested in this. So for me, that was not exciting reason to like mixture models. The reason I loved mixture models is the following question. So suppose you are a fan of hockey, right? And then you know this guy, for example, Nikita Kucherov, right? And you know he scored 33 goals last season, right? And you want to predict how many goals will he score in the next season. So, you know, that's a question I personally get excited about, right? So like, how do you predict this? And okay, so let me just leave it hanging, and then maybe I'll tell you. So I have a few slides at the end to tell you about empirical Bayes and how NPMLE. But for me, this is the reason to learn about NPMLE. However, the traditional statistical reason is in mixture modeling. Okay, so what's the setup? So we will have a parametric family of densities, right? P sub theta. As usual, and we have right. So theta ranges over the space of over the space of capital theta, right? And then on the space of parameters, right? On the parameter space, there is some mixing distribution pi, right? And so then we can form this average density, right? Which will be denoted from my talk as P sub pi, right? Which is just the average of this densities over the mixing distribution, right? And the goal is that, okay, I give you samples, IID samples from P sub pi, and your job is to learn pi, right? So in some sense, I mean, you should think of pi as a real parameter here, right? So pi, this density is this potentially infinite dimensional parameter. Okay, so right, so the simplest example which we will talk about in this in my presentation is the Gaussian location mixture model, right, where this family of distributions just shifted Gaussians, right? So P sub theta is Gaussian centered at theta. So then the mixture density P sub pi is nothing else than just a convolution of your Bayes distribution pi with the phi, right, where phi is the standard Gaussian bump, right? So okay, so this is the way we sort of teach it in the intro stats classes, right? If Pearson crab data, for example, right, you want to estimate a two-component Gaussian mixture, right? So you postulate that the mixture distribution only has, for example, two components, right? And then you can write down, right? So then it becomes a parametric model with three parameters, right? Two weights and two locations, and the weights are constrained to sum to one, right? So you have a three-dimensional parameter space, right? So then you should say, hey, so I observe, right? So once you fix the number of Gaussian mixtures, it becomes a parametric inference question. So everything should be easy. Well, the issue here is that if you try to do maximum likelihood, right, then the likelihood function becomes very non-convex in terms of this parameterization of weights and locations. So there are lots of tricks how to do this in practice. And I mean, the main trick is known as expectation maximization. But here we are interested in non-parametric modeling, right, where we don't restrict the number of components, a priori. So what are the non-parametric methods? So okay, so there are several, right? So I mean, one of them is a method of moments, where you just you learn pi by saying, okay, let's match the moments, empirical moments of the distribution, right, with the moments of the mixture density corresponding to pi, and that's how I will infer pi. The second important methodology is the minimum distance estimator, right, where you estimate the density by minimizing the distance between mixture density p sub pi and the empirical observation density. And the final methodology, which I will talk about, and it was introduced by Kiefer and Wolfowitz, is a non-parametric maximum likelihood. Now, before I describe what is NPMLE, I just wanted to mention, okay, I like to say this, yeah, so that, the first two methods are not quite tuning parameters free, right? So in the method of moments, you have to postulate arbitrarily how many moments are you going to match, right? And the minimum distance estimator, again, you have to pull out of a hat some sort of a distance, right? I mean, you use TV, somebody else uses Hellinger. Why this, why that, right? So that can always raise questions. So in some sense, NPMLE is really nice because there's nothing to defend there, right? It's just completely stated, as is. So there's nothing. Okay, so what is the NPMLE? So NPMLE is the following problem, right? So you formulate likelihood function, log likelihood function, right, which is a sum over I of log likelihoods for this density p sub pi, right? Remember, pi is a parameter evaluated at the data points, right? And then you say that I want to maximize this over the choice of all priors. So this is the key idea here, right? That you don't restrict the number of atoms, right? You just say, okay, there is the space of measures on probability measures on theta, and I will just maximize brute force, over all possible measures. So, okay, so why is this? First of all, why we do this is because the k component mixture problem, right, where you restrict the number of components, right, is finite dimensional, but it's very non-convex. So when you do this relaxation, right, if you like optimization, right, you could say that what you're doing here is you're doing this over parameterization or convex relaxation, right? You make the problem infinite dimensional, but suddenly convex, right? So then you hope that maybe it becomes easier, right? So that's the reason we like it. Okay, so actually NPMLE has connection to minimum distance estimation, right? I mean, you can think of estimating, right? So, I mean, maximizing likelihood is no different from maximizing the KL divergence between the empirical and p sub pi, right? So in some sense, you could say that NPMLE is a particular version of minimum distance. Now, if you write it in this way, then there is actually a connection to ray distortion theory, because minimizing KL divergence in the second argument is equivalent to solving a ray distortion problem under the special penalty. And if you know what ray distortion, I mean, I'm an information theorist by training. For me, it's an exciting connection. For you, it might be less exciting, but I really like this. So and also, like Jonathan Weed and Philippe Regolet, right? So they proved in 2018 that you can also view this problem of maximum likelihood as a form of minimizing transport distance with entropy penalization, right, with an entropic optimal transport. So in some sense, there's lots of ways you can think about NPMLE, right, and be excited about NPMLE. So let's look at some algorithms, right? So it looks hopelessly hard problem to solve. So what is known about this? Okay, so first of all, I mean, there is a simple argument here that you can see that, in fact, I mean, solving this maximum likelihood problem, sorry, not the argument, but there is this iterative algorithm which later was named expectation maximization, right? I mean, so one of the discoverers of expectation maximization is this paper by Richardson, who proposed exactly this alternation. And then in information theory, when you solve ray distortion problems, you also use some kind of expectation maximization. We call it Blehut-Arimoto. In statistics literature, again, I cannot possibly talk about, even 1% of papers here about NPML. It's a very popular topic. But just what's relevant for my talk today is results in one dimension. So in one dimension, we know that several things. That, for example, the solution under very mild conditions, the solution to NPMLE problem is always unique, which is very good in use, right? And the second is it's discrete, right? So even though you over parameterize like crazy, right? You say, I am allowing any possible mixing distributions, continuous densities, and so on. The NPMLE will be smart and it will only return discrete mixtures, right? And so this is the standard results. Anyway, so in stats, there's also this cool other iterative algorithms which are not EM style, which are known as vertex exchange methods and so on. So anyway, so right, and then there's lots of applications of NPMLE for questions like density estimation using NPMLE and so on. So okay, so right, so again, just to recap, NPMLE is very nice algorithm, right? A very nice estimator. It has no tuning parameters. Seems like it should be easily solvable because it's convex. Then there's famous results, right, by Zhang and recently by Berkeley group, Saha and Gontaboina, about quality that shows that, I mean, if you are into density estimation, then NPMLE almost gives you near parametric rate in mixture models. And as I said in the beginning, right, for me, personally, the most exciting connection is that, you know, it works really well in empirical Bayes. Okay, right. So what am I going to talk about in this presentation? So you see, I mean, since we are over parameterized so much, right, the wisdom that we are taught in every sort of from day one, right, in ML and stats is that, I mean, when you over parameterize, there is overfitting. So you sort of overfit to data, and then maybe it's a bad idea, right? And so that's the topic I want to discuss in today, right? So does NPMLE really overfit much, right? So so if for example, if your real distribution is, say, you know, has a few components, right? Let's say one, I mean, it's a pure Gaussian or maybe two component Gaussian mixture. So what's the typical size of the model that NPMLE returns, right? And and that's sort of the surprising part here, right? That despite, you know, thousands or hundreds of papers written on NPMLE, this is not a question that people answered before. All right, so this is right. So we're entering the main stuff, right? So, okay, so let's talk about optimality condition, right? So we have this objective function L of pi, right, parameterized by the distribution, and we want to maximize it, right? So okay, so let's write down the simple variation. Let's do the simple variation, right? If pi hat is your current estimate, let's perturb it by a delta function at some location theta, right? So then the likelihood should decrease, right? If you are, or non-increase if you're at the optimum. So you can differentiate in the small perturbation, and you get this funny, you know, funny condition that if pi hat is optimal, then this derivative, right? So this is the sum over n of, you know, p sub theta xi divided by p pi hat, right? Should be less than 1, right? So some function of pi hat should be less than 1 for every theta, right? So this is how KKT conditions look like here. So you can use some sort of tricks to show that actually here they're necessary and sufficient. It's not very surprising because it's a convex problem, right? Anyway, so right, so this is the condition, right? And yeah, and so now let's do one funny trick here. Let's average this condition over pi hat itself, right? And so when we average over pi hat, you see what happens is that the numerator, right, averages to the denominator, right? And so the average should be 1, from which you conclude that since this is a function which is upper bounded by 1, right, and when you averaged it, you got exactly 1, it has to be equal to 1 on every point in the support of the mixing distribution, right? So which says that the support of the NPMLE should be contained in the global maximizers of this function, right? Or right, even more, this is a smooth function in our case, right? In the case for models which we will consider, this is a smooth function, so you can also differentiate and just count the number of critical points, right? So that's the idea here, right? So this is how we're going to bound the complexity of the model returned by NPMLE. Okay, so let's try to apply this for the case of Gaussian mixture. So if you plug things in, then it turns out that here this function d of theta becomes up to constant equal to the Gaussian mixture itself, right? So this is the interesting part here, right? So we are computing the Gaussian mixture, right? And then with n components, right? Which are located at exactly at the data points, right? So x1 up to xn are your data points, and you have Gaussian mixture located with bumps located on the data, right? And the question is, how many critical points can this n Gaussian mixture have? So this is actually a classical topic, right? So for questions like this, so already Paul and Seguin showed that the n Gaussian mixture cannot have more than n modes, right? And in particular, so putting these two together, right, we derive this result that for Gaussian mixture models, wherever you put your points, right, it's completely deterministic result, right? You put your sample points anywhere. They don't have to come from any distribution. You can just put them by hand, right? Your NPMLE will, well, first of all, it's unique in any case, right? And the second thing is it will always return at most n, right? So the NPMLE distribution will have at most n components. So this is super important, and this is a classical result in this literature by Lindsay, right? And so, okay, so I will demonstrate very quickly numerically that it's actually tight. You cannot improve this, and which is also very sad, right? Because you have n samples and you feed 2n minus 1 parametric model to it, right? Which sounds like a bad idea, right? So that's right. So that's something like you would not be excited about, right? And yes, but then we have, I mean, many practitioners actually observed that, you know, when you feed NPMLE to actual data in real life, right? So then the number of components is significantly smaller than n, right? And then actually one of them, Koneker, I mean, the famous guy, right? Econometrician and statisticians. And so he actually played a lot with the data, and he conjectured that the number of components is typically, I think he said square root n or n to the 1/3. So we'll talk about it in a second. So, okay, right. So our question for this talk is, if the data is random, what's the typical number of components in NPMLE? Okay, so here's a simple experiment, right? So I put this is to demonstrate that the Lindsay theorem is tight in the worst case, right? So I put the samples equispaced. These are the red dots, right? Which this is where the samples live, and then you run NPMLE, and it returns this density. You can see that it has, you know, the number of components I think is 11, and it's 11 mixture, right? And we have 11 samples. So if you equispace the samples, you get, you know, far apart. Of course, you get this model from NPMLE. So it seems like Lindsay cannot be improved, right? So it's bad news. But the good news is that if you draw some typical samples, right? So then the NPMLE, this is again 11 samples, but distributed more like you would expect from two-component Gaussian mixture, right? And you can see that here NPMLE actually returns a two-component model, right? And so that's the effect that we wanted to understand with Yihong in this work. All right, so before sort of doing any theory, let's do the simulation, right? So we started with the true distribution, which is single component Gaussian mixture. We draw 10,000 samples, and we ran NPMLE, and we plotted the histogram of how many components it has, right? Remember, Lindsay says that with n samples you can have n components, right? And here we're plotting the histogram. You can see that most of the time we get like, you know, 6 to 14 components, right? In this, so from 10,000 to 6 to 14 is a huge reduction, right? And so the question is, and actually these simulations are very tough to do because NPMLE is very finicky to compute, right? Because I mean, you're looking for some very discontinuous property of the distribution, now, namely the count of the number of supports, right? The support, right? So it's a very discontinuous property of the distribution, and so it's very tough, and that's why maybe previously, right? So people, when they try to plot this as a function of n, it's hard to guess its behavior, right? So okay, so what's our main result? So our main result applied for Gaussian mixtures is the following. So there exists some absolute constant C0, which you know, you can see that these are the two faculty on the paper, right? That we are so lazy we didn't compute this constant, right? We'll do it eventually, right? But it's nice constant. It's like 6, something like this, right? So it's not like Ramsey number or anything, right? So there exists some absolute constant C0 such that no matter what sample you feed to NPMLE, you never get the support bigger than C0 times the range squared, right? So that's the main thing here. And in particular, if your mixing distribution is subgaussian, right, then with overwhelming probability, this range will be square root log n, right? So when you square it, you get log n, right? So then this proves that with overwhelming probability, if your true model, let's say, is compactly supported or subgaussian mixture model, then you never get more than log n components. So in some sense, that's the sort of the main thing you want to remember from my talk, that people conjectured some polynomial behavior, right? The worst cases, and the typical is log n. That's very cool, right? I thought. Okay, right. So oh yeah. So and then I only present on the slides the Gaussian location mixture, but actually our proof also works for general exponential families under one annoying condition, which maybe I'll have some time to talk about later. That the tail, so it applies to any single parameter exponential family as long as the tail decays x to the minus slightly faster than exponential. So for exactly exponential, that's an open problem. We don't have a result on the number of atoms for the exponential family mixtures. Okay, so let me see how I'm doing on time. Okay, so right, so maybe let's spend some time then thinking about what are ramifications of our result. By the way, Ilya, so this is 45-minute or 1 hour talk? I forgot.
1 hour. 1 hour.
1 hour. Okay, good. Okay. Yeah. Okay. So let's ask questions about optimality of log n, right? So first of all, can you maybe improve log n, right? Could it be log n, right? And instead of log n, well, the answer is no. Why? Because of the following indirect argument. So first of all, you can ask yourself the following question: how well can, for example, Gaussian N02 can be approximated as a mixture of N01 Gaussians, right? So how many atoms do you need? And you can prove that, well, you need e to the minus, right? So, I mean, with k atoms, you get exponential in k approximation and no better, right? Okay, so, and now this implies the following, that for any estimator, also H stands for Hellinger distance, I'm sorry, right? So for any estimator, which estimates Gaussian N02 density with polynomial in n speed in Hellinger, right? The support of this density should be at least log n, right? So just to put together these two facts, right? Okay, and then finally, the third fact, which I'll talk about in a second also, is that Zhang in 2009 proved that NPMLE serves as a very good estimator of the density p sub pi itself, right? So if you draw samples from a truly from true Gaussian mixture, then the Hellinger distance between NPMLE estimate and the true estimate is log n over square root n. So it's particular as poly n, and therefore, right, it's not possible for NPMLE to have less than log n atoms. Okay, so log n is tight in the worst case, right? Okay, so what about, so now let me explain, and this is the main this is the conceptual part, right? I'll tell you about the proof also and the details, but the conceptual message here is very peculiar, and that's what I want to draw your attention to. And so first of all, why log n is super important and natural. You see, I mean, if you take any subgaussian distribution, then you can always mimic it by a k atomic distribution, right? With Hellinger distance, which is little of 1 over square root n, right? So you give me any mixture model, right, where underlying distribution is continuous, maybe uniform, right, or Gaussian, anything, right? And then I can match it, right? I can model it, I can approximate it by a k atomic distribution with log n atoms, right, up to polynomial, right, in such a way that Hellinger becomes little of 1 over square root n. Now, why is it important to have little of 1 over square root n? Because this means that the sample drawn from pi or the sample drawn from p sub pi is statistically indistinguishable, right? So you can couple the two together, right? And with overwhelming probability, they will produce exactly the same sample, right? So which means that from the point of view of statistical estimation, right, there's never any reason to go beyond log n, right? And somehow NPMLE, even though nothing encourages NPMLE to select a simple model, right, it somehow zooms in, right, at exactly the right scale here. So it never overestimates, right? It just stops at exactly the right order of magnitude. And this is why we call this property the self-regularization. So let me again put it in the model selection kind of language here, right? So we have a sequence of models growing in complexity. In my running example, right? This is a this is a k atomic distribution, right? So M sub k is a collection of all mixture densities corresponding to k atoms, right? And we know that its statistical degree, this is not a standard term, this is what we introduced with Yihong just for this discussion, right? So the statistical degree is log n. In what sense? In the sense that if you take any density from the last model, from the M union of all of this, right, there exists an element from the log n, right, from the model at tier log n, such that it's statistically indistinguishable from that one, right? So in some sense, this infinite tower of models has a natural upper bound, right? It stops after log n. It doesn't exist after log n, right? And the surprise here is that NPMLE automatically selects the density estimate from this upper bound, right? And that's what we call self-regularization, right? So that's the peculiar property, right? And the point again is that the wisdom, the standard wisdom is that what you do is you do maximum likelihood over a sequence of models, and then you penalize for the model complexity, right? That's the, I mean, if you remember, Akaike information criterion, BEAK, right? Bayesian information criterion, MDL principle, right? All of these are incarnations of this principle that you shouldn't run maximum likelihood over very fat models because they will overfit, and you should penalize a little bit. And somehow NPMLE in this particular case succeeds without doing that. Okay, so this is the, right, so this is what I wanted to mention about that stuff. Okay, and right, so if you're a model selection person, then what the statement here is that if you run the NPMLE over parametric sequence of models, right? That's how it's done almost always, right? In the Pearson-Krebs stuff, right? So then this function, the likelihood or max likelihood over k Gaussian mixture models, right, becomes flat after log n, right? So it grows, and then becomes just flat. And this means that no model selection method will ever select a model bigger than log n, right? So that's the thing here. Okay, right. So there is also a connection here, right, and the analogy with so-called shape constraint NPMLE, right? I mean, the other big topic in NPMLE is how do you do, let's say, estimation of the monotone density, right? And then there's this famous Grenander estimator, which is exactly NPMLE, right? And it turns out that there you also get the complexity of the model, right? You run, you have data, right? And you try to estimate density by doing NPMLE over all possible monotone densities, and somehow you return only the densities which are piecewise constant, right? And the number of pieces grows. Okay, it's not exactly known how it grows, right? It's upper bounded by n to 1/3. In some special cases, is known to be log n, but there seems to be some relation, but we don't know what the exact relation is. Okay, but again, it's in the same spirit. Okay, now here's why we were interested in this in the beginning. So there's this famous result of Zhang, right, which I mentioned several times already, that NPMLE, if you are doing the Hellinger, if you are interested in doing Hellinger estimation, estimation of density under the Hellinger distance, then it gives you upper bound of log square n over n, right? And here was our thinking. Okay, so first of all, his analysis is sort of the tour de force of empirical process theory, right? You notice that NPMLE is the max of some Gaussian process, and then you apply, the usual tricks. And so you need a lot of metric entropy bounds, actually bracketing entropy bounds, and so on. So, but I mean, we started with a very simplistic point of view. We said, okay, look, the quality of Hellinger estimation with d parameters, right? If you had d parameters, you'd expect something like d over n quality, right? And if NPMLE returns much fewer parameters than, right? If NPMLE returns C log n, right? Then let's just be stupid and think that, okay, then this means like our problem is like, log n parametric problem. And so let's just plug in this mindset, right? At d over n, instead of d, we plug in log n over n. So we should get this bound, right? And this would be exciting. Why? Because it would match with the lower bound, with the lower bound known for density estimation, which is log n over n, right? And it would close this gap. Well, unfortunately, when we execute the strategy, we lose log n factor. So we didn't beat Zhang by this method. But our proof is, doesn't use any metric entropy. Actually, okay, it uses some other results in K-Gaussian mixture estimations, but K-Gaussian mixture estimation, but not NPMLE. So we don't need to analyze NPMLE here. So we sort of can bootstrap our result plus some result of in computation for parametric MLE implies this. Okay, implies the result of Zhang. So in some sense, it kind of a little bit at least explains why the rate is near parametric here. Okay, right. So yeah, so I wanted to talk a little bit about this cartoon example, but I think I probably don't have time. So let me skip this. Okay, so let's talk about the proof, right? Okay, so first, let's as a warm up, let's do the case of Poisson mixture instead of Gaussian. Okay, so for Poisson, right? So our mixing distribution, sorry, our density is just p sub theta of x is Poisson theta, right? And it's discrete, right? So we can compute the gradient, or we get the same function dp hat of theta, right? And we can compute, right? So then we can see that it has a very funny and pleasing property, right? That as a function of theta, it's just e to the minus theta multiplied by a polynomial in theta, right? So that's the amazing. Remember that observations in the Poisson model are integers, right? So it's theta raised to the integer power, right? And so it's a polynomial superficially of degree n, but realistically of degree x max, right? Because that's the maximal observation here, right? And okay, so then, and remember that we know from the KKT conditions, right, that the NPMLE must be concentrated on the points which are maximas of this polynomial, right? So a polynomial of degree r cannot have more than r minus 1 maximas, right? Because you differentiate and take it to 0, right? And so that proves that, right, that this degree, so that in the Poisson case, right, you cannot have more than x max, right? So basically, the number of atoms of pi hat of NPMLE cannot be more than x max, and because by sub-exponential bound you get log n, right? So that's the idea here. Actually, there's a better proof which shows that the number of atoms is always upper bounded by the number of distinct values. So right, so if you only, for example, right, if you get a sample where one of the samples is 1000 and the other samples are all 1, 2, 3, right? So then you can upper bound by 4, not by 1000. Okay. Now the reason this does not work is because for Gaussian d of theta is not a polynomial, right? And then so we cannot apply this reasoning. Okay, so actually, if you try to apply this reasoning, you only get n, right? So it's not a polynomial, but it's what's known as exponential polynomial, and then you can still apply the reasoning, and it gives you n as an upper bound.
Sorry, Yury, what was this comment about multiplicities? What did you say? That the number of roots is what is a real upper bound? That's what you say?
So yes, so okay, so the thinking here is the following, right? So so you have this function d of theta, and the support of NPMLE is concentrated on the maxima of this theta, right? Notice that this is a function which is unknown to you, right? Because it depends itself on the optimum NPMLE distribution, right? But it's some polynomial, right? And you see that this polynomial has degree x max. So it cannot have too many maxima, right? Because it's a low degree polynomial, right? And so that's how you infer that, so therefore, right, the density should, the mixing distribution returned by NPMLE must have at most x max roots. What I said is that there is a different argument which shows that instead of an upper bound of x max, you can upper bound by the number of distinct elements. Yeah, and that bound is true for any exponential family, not for Poisson. But it's a different argument, not related to polynomials. Yeah. Okay, so right. So okay, so let's see what do we have for Gaussian, right? So for Gaussian, we get this right. So this d of theta function is itself a Gaussian mixture, right, of n bumps, and it's a Gaussian mixture located on between x min and x max, right, between the minimal and the maximal sample, right? So then what we need to prove, right? So this reduces to a very nice analytical question, right? So we started with statistics, and now we are into the fun analysis question, very fun puzzle, right? So what is this puzzle? So I give you the interval minus AA, right? And you can put locations of your Gaussian bumps, right? And I give you arbitrarily many Gaussian bumps, right? So you can scale them up and down, right? They are all of the same width, 1, right? And you can place them anywhere in this minus AA, right? So that's the game we're playing. And the question is, how many different maxima can you create by packing these Gaussians, right? So okay, so let's play this game. So let's start with the interval something like minus 2, 2, right? And let's put 2 bumps at locations minus 2 and 2, right? So you can see that you created 2 maxima here, right? Okay, so since we're trying to pack a lot of these maxima, right? So let's bring them closer. So we put this maxima at minus 1/2, minus 1.5 plus, right? We still see two maxima, right? But once we put them at the critical distance of minus 1, 1, right? So what happens is the 2 maxima merge, right? And so you can see that even though I give you, you can place arbitrarily many Gaussian bumps, if you place them too close, the maxima merge, right? And so this becomes a fun puzzle, right? Sort of like extremal combinatorics kind of puzzle, right? It's a packing problem. How many Gaussian bumps how many maximas can you create in the interval, right? And I hope this argument, right? Okay, so this is how, 11 mixture would look on a bigger interval, right? So you would create a lot of ripples, but again, they're sort of equispaced, right? So I hope from this argument, you're convinced that the intuition says that you should be able to create something like order A, right? Because you pack them, right, at this distance, right? There is a critical distance of 1 when the bumps merge. So you should be able to get order A. Well, it turns out the answer is A squared. So that's, so I don't have good explanation why, but, right, so what we proved is that, so this is the key technical result here, right? That if you have any distribution supported on minus AA, then the Gaussian convolution has at most, some universal constant C0, which again, we were lazy to identify, but it's nice, right? Something like, let me say 6A squared critical points, right? So that's, right, so that's, yeah, and this is tight actually, right? So you can create A squared bumps, order A squared bumps for large A. Okay, so how did we prove this? Oh yeah, so first of all, I mean, we were totally shocked. It actually happened in the PFL when we get, I mean, we already were writing this up, right? And then we get an announcement for the talk on some amplitude constraint channel capacity. We're like, okay, whatever, right? I mean, and then the talk was canceled, but we still decided to read the paper because one of our friends, Semi Yagli, and so we read the paper, and actually deep inside they also extract the same bound, so also A squared. But they were thinking in the same way, right? They said, hey, but our bound should be improvable to order A because you cannot pack this many heights, right? I mean, and yeah, so our lower bound is actually very nice. I mean, it's what you do is you just you take a uniform density, and then you add a sinusoid. So this is the mixing distribution, which right. So the speed, sort of the frequency is order A, and the interval is of order A. So you get order A squared maxima after convolution. So this is the simple construction. Yeah. So this is just a cartoon to show you how it would look like, right? From sort of, if you zoom out, it will look essentially flat, but when you zoom in, there's tiny little ripples there on top. Yeah. And then there's also a different construction people just published. Not using sinusoids. I mean, we like sinusoids because it also works for many other exponential families. Okay, so how do we prove this cool result that you cannot pack more than A squared critical points or maxima? Okay, so the idea is roughly, okay, I'm trying to explain this here. So, I mean, what we will use is some tricks in complex analysis, but let me explain how they enter the equation. Right, so if you have a polynomial, so imagine a polynomial with a bunch of small roots. Like here, these are roots, the fourth roots of unity, right? Right, and this is a polynomial, right? And then it has no other roots, right? So when you go far away on the complex plane, by this factorization, right? Since this polynomial should factorize like this, right? What you see is that it should grow roughly at z to the n, right? So it will grow very fast, right? If you have n roots which are small, right? So then when you go far, it should grow fast, right? The more roots you have, the faster it will grow at infinity, right? And this principle actually works for all holomorphic functions, right? Holomorphic functions with a lot of zeros tend to be very wild, right? So because they're highly oscillatory, as you can imagine, and then holomorphic functions, if they are oscillatory somewhere, they will grow insanely fast at infinity, right? So that's the principle here. Okay, so now there's this guy, Jensen, who not only proved the inequality we all love, but also proved the following formula, that this is true for any holomorphic function, right? If you sum logarithms of all the roots inside some disk of radius r, then it's exactly equal to to the integral of the function on the boundary, of the log of the function on the boundary, right? So basically, I mean, this is one thing I want you to remember, that information about the roots, their number and their locations, right, is encoded in the, of course, in the boundary values of the function, but also there is a very nice expression, right, which you can leverage. Actually, we don't in the paper. I mean, I don't only do it for presentation. In the paper, we had to do something slightly different, but anyway, so if you read it, okay, so right, so and then from the above formula, you can easily see that if inside this large disk of radius capital R, there's a small disk of radius little r, right, then you can bound the number of zeros of G inside that radius by something like the log of the magnitude of the function on their large radius, right? So that's the cool idea here. Okay, right. So let's right. Notice that again we're bounding the number of zeros by the log magnitude, right? So that's not exactly the same. I mean, when we started, the first thing we tried was the other formula, right, where you bound the number, where for any analytic function, right, you can bound the number of zeros inside the circle is exactly equal to the integral of the log of derivative, right? So of f, of derivative of f, right? But here we don't have a control on the derivative, but we have control of the function of. So anyway, so this was the trick. Okay, so let me show you how the proof works. Okay, so we are working with the mixture, right? Pi convolve phi, where pi lives on some interval minus AA, right? And this is the mixed density P of X. We have to localize its maxima or critical points, right? So when you do differentiation, this is a standard Gaussian derivative trick, right? Which shows you that, okay, actually this derivative can be written as conditional expectation. And since U takes values inside, right, the interval A, right, because U is distributed according to pi, sorry, right? So then this derivative, right? So the derivative becomes either positive or negative, right, outside of the interval minus AA. So this means that all the critical points of density should be on minus AA, right? If you convolve pi with phi, all the critical points are in this interval minus AA. Okay, so then, okay, we need a lower bound, right? So remember in this previous thing, there is also the value of the function. I mean, it should be scale invariant, right? There's a number of, you're bounding number of zeros, it should be scale invariant quantities. So you need to normalize by the value of the function at the zero. Right, and so what we did, right, so I mean, there's a simple upper bound for the derivative at some faraway point. And there's also a simple upper bound on the complex circle, right? Because, I mean, you can see that this is, right, so this is expectation of something like e to the x square, right? So you can bound the growth as e to the magnitude a square, right, on a large circle of radius a, right? So this is what we did. And from Jensen formula, you immediately conclude that not only p prime has order a square zeros on the real line, it actually has order a square zeros even in a huge complex circle, right? The circle on the complex plane. So that's the trick. And again, for exponential family, we get a slightly different proof, but the idea is roughly the same. Okay, so right, so this is how our proof worked. I don't know, maybe it's a good time to ask for some questions.
So do any of these ideas work in the multidimensional context?
Very good. This is all open questions. Yes, I'll tell you in a second. Yes, it's a fantastic question, John. And unfortunately, I mean, we tried and we failed. So yeah, I mean, one reason is there's no Jensen formula. I mean, it's sort of the simple reason, right? I mean, there is no such an easy way to count the number of, first of all, what is a critical point, right? I mean, you can have critical manifolds there and so on, right? So then, so it's, anyways, it's very tricky, and I'll mention it in a second.
Okay, great, thank you.
Yeah, so there's, yeah. Okay, unfortunately, I didn't prepare a slide, but there's fascinating question on algebraic geometry, which even for Poisson mixtures in 2 dimension, which results, I mean, okay, I can mention this, yeah. Essentially, okay, our conjecture is that you should be able to get log n to the d. And the only thing you need to prove is that certain polynomials do not share a common factor. So you have data-driven polynomials, and of course, I mean, unless there's, you know, some kind of, you know, solar eclipse situation, right? That they shouldn't get a common factor between them. And if they don't, then you get the estimate of log n to the d automatically for all the models we get. And this is a dream result because it also translates into cool results about density estimation in d dimensions, right? In Hellinger distance, right? So
So do Gunter do they have the right rates for density estimation for, I mean, do they know that what the NPMLE achieves for the higher dimensional case?
Yeah, so I think I mentioned this somewhere later.
You can keep going, that I don't
want no, let's see. So I think or maybe this is in the paper. Yeah, okay, sorry, this is in the paper. I mean, they get, yes, so they get log n to the d, but I think the constant is very bad. So it's not d, it's like log n to some power of d. So I don't remember exactly, but yeah. Okay. Anyways, okay, so let me say, right, so some of the limitations of our stuff. So first of all, I mean, the biggest upset for us was that we couldn't solve exponential mixtures, and somehow our method is fundamentally flawed here. And of course, I mean, this is not just idle curiosity, right? I mean, exponential mixtures are an important you know, model, and right, and so our analysis yields a bound, which is, you know, the support of NPMLE is bounded by the ratio of max to mean. And of course, if you draw your samples from exponential 1, then the minimum is going to be order 1 over n, and maximum is log n. And you can see that what kills you is the minimum sample, right? And so and somehow, yeah, so there's lots of cool questions. Actually, in the paper, we formulate a complete, so if you don't care about mixtures of exponentials, you don't want to do any statistics, there is a completely cool self-contained analytic question. So similar to how I was asking about packing many critical points of the Gaussian, right, by displacing the Gaussian locations, right? The mixture of exponentials question reduces to packing critical points of something that is called Gompertz density. I'm sure none of you have ever heard about Gompertz. I didn't. I thought we invented this distribution, but it's a distribution which has doubly exponential tail on one side and exponential side on the other side. So it's asymmetric. And then you play the same game, right? I give you the interval minus AA, and you have to pack, right? And the conjecture, okay, in the paper, we said that it's theta A, because we were dumb, and then Fyodor Nazarov actually immediately pointed out that our own lemma proves a square lower bound. So later, the sinusoid construction. So in the paper, you can think of this as a typo. I mean, really, we want to poly A bound on exponentials. Okay, but right, and then the question is, we don't know actually. Yes, maybe for exponential mixtures, the bound is not going to be of order log n, in which case it's not going to be self-regularizing. Okay.
Can I ask one question about that,
Yes,
Yury?
yeah.
Are the right rates for do people understand the rates in Hellinger for the NPMLE for these exponential mixtures? I mean, is there a conjecture you make on those grounds?
Good question. I don't remember. Yes, I don't remember. So that's something I don't know. Yeah. And again, I mean, right. So I mean, Hellinger estimation, right? It's equivalent, right, to metric entropy bounds, unless you care about NPMLE, right? So I don't know if people studied, right? Because you understand, right? NPMLE could be a bad estimator. We don't know, right? The optimal estimator, the rates are known, right? But the how NPMLE performs. I don't know if somebody studied this. Yeah. So, okay. So the second actually cool thing, again, it will be related a little bit to the stuff I will mention slightly later. But now, suppose that you know that the true mixing distribution, this is the most interesting case, is exactly, right? It's not 1 subgaussian, but it's actually -1, 1, right? It's compactly supported, right? So then you can calculate that the statistical degree reduces from log n to log n over log n, right? Okay, I know you guys, I mean, when I was younger, I was always thinking like, okay, you know, whoever clears logs is just, you know, has nothing else to do in his life. Maybe I'm just now at this, you know, at this stage in my career. But I mean, we really spent, I would say 80% of this work was spent on this question because we quickly derived all of this log n stuff, but we tried to solve this and it failed miserably in many different ways. So this is a super cool open question, right? So the correct model, so any mixture, any completely supported mixture can be modeled as log n over log n atomic mixture, right? And then the question is, if you run constrained NPMLE, will you actually get log n over log n atomic distribution or not? So this requires only one tiny modification of our proof. So before we asked about the totality of the real roots of the Gaussian mixtures, right, of this number of critical points. Now we're just asking about the number of roots inside the interval -1, 1, right, inside the small interval, right? And the question is, how many roots can it have? Well, it turns out we cannot answer this. So so we can bound tightly, right, the number of roots in a large circle, but we can never bound in a small circle. So that's the issue here. And we spend a lot of time. Actually, there is a whole other paper we wrote on just showing out of this effort why our current strategy does not work for this method. Like our current strategy extracts the maximum, the best bound, and it's log n. And so there is, anyways, yeah. So what we proved is that, remember, we reduced. So the actual mixture, right, has weights which is 1 over p pi of xi, right? And this p itself is an NPMLE. And we completely ignored this when we bounded the number of maxima, right? We said, whatever, this could be any weights, right? Any n weights, let's just bound them. So this is the strategy which provably fails. You somehow need to prove that these weights are very special themselves, right? And then so this was the interesting. Anyway, so I probably spent too much time on this. I really want to show you empirical Bayes. Yes, so right, in d dimensions, there is right, so there's this issue that, first of all, n Gaussian mixtures, right, can have n to the d maximas. So here's John. So here's a little bit what killed our hopes. So we started talking about Poisson. As I said, it reduces to some cool question in algebraic geometry, right? Some random polynomials should not share a common factor. It looked like we could do this, and it's not very hard. I still think we can do this. Just need to think a little bit. But then we realized actually there is a fundamental distinction. NPMLE is always unique, no matter where you place it, right? It could be deterministic locations, right? For Poisson in 1 dimension. But on 2 dimensions, if your samples are lined up, for example, on a diagonal, right? So you have a 2, right? You have like Z2 plus, right? And if they are lined up on a diagonal, then you have many solutions, right? So with some small probability, basically, the NPMLE in 2 dimensions for 2-dimensional Poisson is not unique, right? So already uniqueness is killed. And in some sense, now you really want the typical behavior of these random polynomials. Anyways, okay. Yeah, so the algorithms is an interesting question by itself. So I think for you guys, it might be interesting. So let me just, so Ilyas, can I do 2 minutes primer on empirical Bayes? Okay, so because this is, I mean, this is what drew us originally to this question, right? Okay, so what's the empirical Bayes connection here, right? So the standard question, as I said, right? So you want to estimate Kucherov scored 33 goals this year. How many goals will he score next year? Well, your data set about Kucherov is very limited, right? It's only played 5 seasons. So it looks like you can't predict well from just Kucherov alone, right? But the advantage is that now you have this enormous data set about other players, right? And the question that Robbins asked himself, right? He said, okay, if I have 1,000 other players played in this season, right? And I know how they score, does it help me in estimating how well the Kucherov will play? how well Kucherov will score next season. And the idea is that yes, it can help, right, by sort of, I mean, by doing shrinkage, right? You want to shrink the estimate, right? The natural estimate is that if he scored 33 today, then maybe 33 next season is a natural guess, right? So this is what you would do naively, right? But then you want to shrink this toward the Bayesian mean, right? And what you do is you estimate the Bayesian mean from, sorry, you estimate the Bayesian prior from the other players, right? So that's the idea. This is sort of generalized shrinkage here, right? That's why, I mean, I love empirical Bayes because somehow it's a principled way of doing shrinkage, right? Okay, so right, and the sort of the diagram, yeah. So what Robin said is it said, okay, just to learn the prior, just do some kind of empirical estimation, right? So you have Poisson theta observation for each player, right? And then what you want to learn is what is the prior from which the player parameters were drawn. So do that and then predict based on that prior, right? Just do the Bayesian prediction using that prior. Right, and so anyway, so the point is that Robbins proposed some majestic estimator, which, you know, blew everyone's thinking out of the water, right? Because somehow he would predict the Kucherov's performance based on all other NHL players. So his estimator for his next year performance, right, depends on how other players worked. And this was completely mind-boggling to people because they said, how? I mean, this is independent guys, right? Why prediction for Kucherov should depend? Now today, of course, we understand because he's doing shrinkage, but this came later. In any case, so here's the data, right? So this is 2017, 2018 season. And, you know, so what I'm plotting here is that this is the past season, this is the future season, right? So you see the data for a player this season, for example, it's maybe 33, right? And then you're trying to predict how many he will score next season, right? So the Robbins estimator does the prediction, right? So for 20, it predicts 10, right? For 21, it predicts 32 and so on, right? So this is the dashed line, dashed orange line. That's how it predicts, right? So it's not very exciting, right? But if you run NPMLE and then just plug it into Bayesian expectation, then you get the green curve, which somehow, right, I mean, very smartly learned that there is a natural upper bound, right? So even if you scored 40, it's very unlikely you will score 40 again next season, right? So it's very nice shrinkage. It does very nice shrinkage. And so these plots, I mean, were done by numerous people over, you know, over 60 years or 70 years since Robbins invented his estimator. And so everybody under the sun trashed Robbins, right? They said, hey, your estimator is non-monotonic. It's chaotic like crazy, right? We don't like you. I mean, it's bad. And so everybody basically improved upon Robbins over the years. And with Yihong, we actually proved that, right. So, I mean, the big question in this field is, right. So what's right. So if you're estimating n parameters, right, and how close can you be to the Bayesian optimal estimator, the guy who knows the true prior of the right, and this is called regret. All right, and the question is, I mean, do all those estimators which were, you know, derived over the years, in particular NPMLE, do they beat Robbins or not in terms of regret? And we proved actually no, that this Robbins, which is so annoyingly dumb, right, and bad behavior. I mean, sorry, it's super smart, but it's behaving so badly, right? It actually achieves optimal regret, right? And this regret is log n over log n squared. Okay, again, I understand your concern, right? You're like, Yury, it's too many logs to be relevant. Yes, okay. But I just want to point out one last thing before I close this talk. For who knows how many years, the goal, the big conjecture was to please prove omega-1 lower bound, right? So this was the big thing. I mean, people worked on this. I mean, there's many, you know, super smart people, much smarter than, you know, than us, worked on this. And so when we started to prove this lower bound, I mean, we didn't expect to get a tight result, right? So we just got this log n over log n squared. I mean, initially it was much worse, but then we improved. And then we noticed that, oh my God, actually, finally we reached the upper bound, which was proved. We reached the lower bound, which was proved to be achievable by people before. So Brown, Granstein, and Ritov. And we did the same for normal means, but there, unfortunately, logs do not match. So so we still have, I mean, still there was a major conjecture to prove omega-1 lower bound. We proved, you know, a much better lower bound than omega-1, but we don't know if it's tight. Okay, I think I can stop here. Yes. So the summary is that we learned that NPMLE somehow selects the models of good size. And I mean, in our paper, there's so many open problems that we should apologize that there's like more open problems than closed problems by the paper. But yeah, and I also advertised this empirical Bayes result, right? And it has connections to NPMLE there as well. Thank you, guys. Sorry, I went a bit over time.
No, I think that was great. Thank you very much, Yury.
Thank you.